This video covers Part 3 of Section 1.2, Logical Equivalence. In this video, we're going to talk about equivalences. Suppose that the compound statement forms P and Q are logically equivalent. This means that for all choices of truth values of their statement variables, P and Q have the same truth values. It follows that the statement form P if and only if Q is a tautology. On the other hand, if the form P if and only if Q is a tautology, similar reasoning shows that P is logically equivalent to Q. We then have the result that P is logically equivalent to Q if and only if P if and only if Q is a tautology. For this reason, any tautology of the form P if and only if Q is called an equivalence. Equivalences, or logically equivalent statements, are important tools for proving theorems in mathematics. In order to prove a theorem, we need to construct a logical argument to show that the theorem statement is true. It may be possible to prove the statement directly. In many cases, however, it may not be possible to prove the statement directly, or it may be easier to prove a logically equivalent statement is true. For instance, suppose we want to prove a mathematical statement which has the symbolic form P implies Q. It may be easier to prove the contrapositive not Q implies not P. Since these two statements are logically equivalent, they have the same truth value. Therefore, if we show that the contrapositive statement is true, it will then follow that the original statement is also true. This observation forms the basis for the method of proof by contrapositive. As another example, suppose we wish to prove a mathematical statement which has the symbolic form P or Q implies R. It can be shown that P or Q implies R is logically equivalent to P implies R and Q implies R. So instead of proving the original statement P or Q implies R directly, we can instead prove the logically equivalent statement P implies R and Q implies R. Since the two statements are logically equivalent, if we show that one is true, then the other must be true. This equivalence forms the basis for the method of proof by division into cases. The following theorem lists some of the more important logical equivalences. The proof of each part of the theorem simply consists of constructing truth tables for each statement form in the equivalence. So for any statement variables P, Q, and R, we have the following equivalences: the double negation property, De Morgan's law, the second De Morgan's law, the negation of the conditional, and the negation of the biconditional. These first five equivalences tell us how to negate compound statements. We've already seen and used these in earlier examples. It's important to have these five memorized. Next we have commutativity of disjunction, commutativity of conjunction, the associativity of disjunction, associativity of conjunction, and two distributive laws. We can either distribute a disjunction over a conjunction or a conjunction over a disjunction. So the equivalences in this group give some basic properties of conjunctions and disjunctions. For instance, the two associative laws tell us that when we have two conjunctions or two disjunctions, it doesn't matter how they are grouped, which means we can ignore the grouping. So we can write the quantity P and Q and R in English as just P and Q and R. For our next group, we have the biconditional law, the contrapositive equivalence, and the representation of the conditional as an OR statement. We've already discussed the biconditional law and the contrapositive equivalence. Both of these should be memorized. The equivalence in N shows how a conditional can be represented as an OR statement. This is included here primarily for completeness' sake. It's not really used in any problems. Next we have five equivalences that are used in proofs. So we have a strategy for deriving the conclusion, Q or R, strategy for using the hypothesis, P or Q, the strategy for deriving a conclusion, Q and R, an indirect approach to using the hypothesis, P and Q, and the strategy for using the hypothesis, P and Q. As their names imply, the equivalences in this last group are used to prove statements of various types, as illustrated in the next example. These last 5 will be important later in the course when we start looking at different methods of proof. There's no need to memorize these now since we'll refer to them as needed. As mentioned above, in order to prove a given mathematical statement is true, we may prove any logically equivalent statement is true. For our next example, so we have for each of the following statements, first translate the statement to symbolic form. Then use one of the equivalences in the theorem to find a logically equivalent statement which may help in proving the original statement. We'll assume here that m and n represent particular fixed integers. So for our first example, we have the statement, if m is even, or n is even, then m times n is even. In order to translate the statement to symbolic form, we'll first define statement variables. So P is m is even, Q is n is even, R is m times n is even. The statement then has symbolic form, P or Q implies R. Note this statement has an or in the hypothesis. Looking over the equivalences in the theorem, we see that the equivalence in part P includes a statement form that has an or in the hypothesis. P or Q implies R is logically equivalent to P implies R and Q implies R. Since these two statements are logically equivalent, to prove the original statement P or Q implies R is true, we can instead prove the logically equivalent statement P implies R and Q implies R. In English, this is, if m is even, then m times n is even, and if n is even, then m times n is even. So the point is, instead of proving the statement in its original form, we can prove this logically equivalent statement. As we'll see later, applying the equivalence in part P of the theorem is the standard approach to prove a conditional statement that contains an or in its hypothesis. For our next part, we have the statement, if m times n is even, then m is even or n is even. Using the same statement variables as in part A, this statement has symbolic form, R implies P or Q. This statement has an or in the conclusion. The equivalence in part O of the theorem includes a statement form that has an or in the conclusion. R implies P or Q is logically equivalent to R and not P implies Q. So to prove the original statement, R implies P or Q is true, we can instead prove the logically equivalent statement, R and not P implies Q. In English, this is, if m times n is even, but m is not even, then n is even.